Good day, everyone. Today, we will be talking about logarithmic functions. But before we start all the solving, let us first define what logarithmic functions are. If you search on Google, you will find that logarithmic functions are the inverses of exponential functions, and I don't think there is another simple way to define it. A logarithm is denoted by the letters log or log. In this example given in Paul's online notes, y equals log base b of x is equivalent to b raised to the power of y equals x. B raised to the power of y equals x is the exponential form, while y equals log base b of x is the logarithmic form. A logarithmic function is a function of the form y equals log base b of x, where x is greater than 0, b is greater than 0, and y is not equal to 1. When learning about logarithms, it is important to know its parts. In the example, log base 7 of 5 equals 2. The subscript number beside log is called the base. The number beside the base is called the argument, and the number that the logarithmic expression is equated to is called the answer.
Let us move on to expressing exponential to their logarithmic forms. Example number 1. 5 to the power of 9 equals 34. When you write this in logarithmic form, you will get 9 equals logarithmic base 5 of 34. This is the inverse of the first example. 5 to the power of 9 equals 34. Example number 2. 80 to the power of 2 equals 1/4. When you write this in logarithmic form, you will get 2 equals logarithmic base 80 of 1/4. Example number 3. 108 to the power of 7 equals 89. In logarithmic form, this is 7 equals logarithmic base 108 of 89. Example number 4. 3/5 to the power of 4 equals 50. In logarithmic form, this is 4 equals logarithmic base 3/5 of 50. Example number 5. X to the power of 9 equals 3. In logarithmic form, this is 9 equals a logarithm base x of 3. Explanation. To express exponential to logarithms, the first thing to do, write log. After writing log, determine the base from exponential equation and write it as a subscript after log. 5 to the power of 9 equals 34. 5 is the base, 9 is the argument, 34 is the answer. After this, write the answer beside log and the base, making it look like this. Logarithm base of 5 of 34. The last step is to equate it to the argument. It looked like this. Log base 5 of 34 equals 9. Now, let us do other way around. Let us give the exponential form of the given logarithmic forms. Example number 1. Logarithm base 5 of 20 equals 3. When you write this in exponential form, you will get 5 to the power of 3 equals 20. Example number 2. Logarithm base 6 of 8 equals 3. When you write this in exponential form, you will get 6 to the power of 3 equals 8. Example number 3. Logarithm base x of 4 equals 7. In exponential form, it is written as x to the power of 7 equals 4. Example number 4. Logarithm base 1/4 of 20 equals 11. When you write this in exponential form, you will get 1/4 to the power of 11 equals 20. Example number 5. Logarithm base 5 of 1/3 equals 2. In exponential form, it is written as 5 to the power of 2 equals 1/3. To solve logarithmic function, you will have to know about the properties of logarithm first. This property of logarithm are found at the omnikit. The first property of logarithm is that logarithm of 1 to any base is always equal to 0. For example, logarithm base 3 of 1 equals 0. Logarithm base 1/2 of 1 equals 0. Logarithm base 10,000 of 1 equals 0. Logarithm base 342 of 1 equals 0. Logarithm base x of 1 equals 0. The next property is that a logarithm of a to the base a equals to 1. If you write this in symbol, you will get log base a of a equals 1. For example, logarithm base 4 of 4 equals 1. Logarithm base 7 of 7 equals 1. Logarithm base 1/4 of 1/4 equals 1. Logarithm base 10 of 10 equals 1. Logarithm base x of x equals 1. The logarithm of a to the power of x to the base a is equal to 1. In symbol, that is log base a of a to the power of x equals x. For example, logarithm base 3 of 3 to the power of -19 equals -19. The logarithm base 18 of 18 to the power of -8 equals -8. Logarithm base 100 equals 2. Logarithm base 9 of 9 to the power of 12 equals 12. Logarithm base 3 of 3 to the power of 10 equals 10. The logarithm of a to the base a to the power of x is equal to 1 over x. In symbols, that is log base a to the power of x. A equals 1 over x. For example, logarithm base 36 of 6 equals 1/2. Logarithm base 10,000 of 10 equals 1/4. Logarithm base 25 of 25 equals 1/2. Logarithm base 49 of 7 equals 1/2. Logarithm base 216 of 6 equals 1/3. The logarithm of the product of m and n to the base a is a equal to the sum of the logarithm of m and n to base a in symbols. That is log base a of m n equals log base a of m plus log base a of n. For example, logarithm of 3x minus 4 multiplied by 3x plus 5 equals logarithm of 3x minus 4 plus logarithm of 3x plus 5. Logarithm of x minus 7 multiplied by x plus 7 equals logarithm of x minus 7 plus logarithm of x plus 7. Logarithm of 2 multiplied 13 and 6 equals logarithm of 2 times 13 plus logarithm of 2 times 6. Logarithm of 2 multiplied 7 x equals logarithm of 2 plus 7 plus logarithm of 2x. Logarithm of 8 1/4 multiplied 17 equals logarithm of 8 1/4 added to logarithm of 8 17. The logarithm of the quotient of m over n to the base a is equal to the difference of the logarithm m and n to the base a. In symbols, that is log base a of m over n equals log base a of m minus log base a of 2n. For example, logarithm base 5 of 9 over 14 equals logarithm base 5 of 9 minus logarithm base 5 of 14. Logarithm base 9 of x over z equals logarithm base 9 of x minus logarithm base 9 of c. Logarithm base 2 of 2/5 equals logarithm base 2 of 2 minus logarithm base 2 of 5. Logarithm base 5 of 14 over x equals logarithm base 5 of 14 minus logarithm base 5 of x. Logarithm base 22 of x over 2 equals logarithm base 22 of x minus logarithm base 22 of 2. The logarithm of a power is described by the equation log base a of m to the power of n equals n logarithm base a m. For example, logarithm base 3 of 4 to the power of 3 equals 3 logarithm base 3 of 4. Logarithm base 2 of x to the power of 3 equals 3 logarithm base 2 of x. Logarithm base 5 of 14 to the power of 6 equals 6 logarithm base 5 of 14. Logarithm base x of y to the power of 3 equals 3 logarithm base x of y. Logarithm base of square root of x equals logarithm of x over 2. The logarithm of a root is described by the equation log base of third root of m equals log base a of m over n. For example, logarithm of 2 to cube root of x equals logarithm of 2x over 3. Logarithm of 10 to the square root of x, logarithm of 2 to the fourth root of x, logarithm of 2x over 4, logarithm of 12 to the fifth root y equals logarithm of 12 y over 5, logarithm of 2 to the sixth root of 13 equals logarithm of 2/13 over 6.
So let us now proceed to expressing logarithms in expanded form. First example, we have log b squared c cubed over d raised to the power of 4 e raised to the power of 5. Since both b and c are on the top, it's going to be positive log b squared plus log c cubed. And since d and e are on the bottom, it's going to have the negative sign, so minus log d to the power of 4 minus log e to the fifth power. Next, we need to move the exponents to the front, which is also the last thing we'll do. So the final answer is 2 log b plus 3 log c minus 4 log d minus 5 log e. For the second example, we have log base 3 of 7x. This is from the product property of logarithm. Take note, we're multiplying 7 and x. What we can do of the product of two terms is to rewrite them as two separate logarithms with that same base by adding the two logarithms so that we can get log base 3 of 7 plus log base 3 of x. Our third example is log y squared x raised to the power of negative 3 and square root of z. We can instantly put this as log y squared plus log x raised to the power of negative 3 plus log square root of z, or z raised to the power of 1/2. Since each logarithms have powers, we need to rewrite them and put those powers in front. So to write it in fully expanded form, we're going to bring the 2 down, also the negative 3, and the 1/2, making it look like this. 2 log y minus 3 log x plus 1/2 log z, and that is our final answer. For the fourth example, we have log 4x over y squared. To solve this, it is recommended to separate them first using the quotient rule and then use the power rule. So it will first look like log of 4x minus log of y squared. Now, we can apply the power rule. Let's rewrite this into log of 2 plus log x minus 2 log y. Our fifth example in expressing logarithmic functions in expanded form is log base 5 of the fifth root of x over y. The first thing to do here is to rewrite this as a power so it will look like this. log base 5 of x over y raised to the power of 1/5. And since we can't apply the quotient rule because our quotient is being raised to the 1/5 power, what we're going to do is use the power rule to get rid of the power. So it'll look like this: 1/5 log base 5 of x over y. Now that we don't have a power over our x divided by y, we can finally separate them using the quotient rule. So our final answer would be 1/5 log base 5 of x minus log base 5 of y. We have to use brackets to understand that 1/5 is being raised to both logarithms. Moving on, let us now learn how to express logarithmic expressions into a single logarithm. For our first example, let's start simple. We have log b minus log w plus log s. Take note, the ones that contain the positive sign will go on top, so that's b and s. So that's b times s. Since w has a negative sign in front of it, it's directly gonna go in the bottom, so our final answer is going to look like this: log bs over w. Example number 2. We have 2 log d plus 3 log e minus 5 log f. The very first thing we need to do is move the coefficient to the exponent position. So it's going to turn into log d squared plus log e cubed minus log f to the 5th power. Now, we can write it into a single log. D and e are both positive, so they're gonna be on top. F, on the other hand, has a negative sign in front of it, which means that 5 to the 5th power goes to the bottom. So our final answer is log d squared e cubed over f raised to the power of 5. Let's move on to the third example, which is log base 3 of x plus 2 log base 3 of x minus log base 3 of 27. We can rewrite this as log base 3 of x plus log base 3 of x squared minus log base 3 of 27. As you can see, we have two logarithms that are separated by addition. When we have two logarithms separated by addition, we can rewrite them as a product using one logarithm. So that will be log base 3 of x times x squared minus log base 3 of 27. And if you remember the rules of exponents, x times x squared equals x cubed. So we can have log base 3 of x cubed minus log base 3 of 27. Now we can see the subtraction or division. So we can finally use the division property, which would be log base 3 of x cubed over 27. This can be our final answer, but when you look at it, we can still evaluate and understand that we can get 3 ways to get 3 to 27, which is 3. So another example that could still be considered correct is log base 3 of x cubed minus 3. For our fourth example, we have 2 log base 5 plus 3 log base 5 of 2. First thing we need to realize is that we should move the coefficients into the exponent position of the number part of the log. So we can write this as log base 5 of x squared plus log base 5 of 2 cubed. We can actually evaluate 2 cubed as 8, so we can rewrite this again as log base 5 of x squared plus log base 5 of 8. We can now apply the product property, which means we can write this as a single logarithm by multiplying the number parts of the logarithms. So this is now log base 5 of x squared times 8, which would be then 8x squared, so this is our final answer, log base 5 of 8x squared. Our last and fifth example is 3 log base 7 of x minus 5 log base 7 of y. We are first going to write this as log base of 7 of x cubed minus log base 7 of y to the 5th. This is the first step. As you can see, it is the quotient rule, since the y to the 5th is after the negative sign, so that means that's what goes to the denominator. So you'll have log base of 7x cubed over y to the 5th. And that is our last step and final answer. Now let's start solving logarithmic equations. With this equation, there are only two logarithms in the equation, so it's easy to get on one either side of the equal sign. We will also need to deal with the coefficient in front of the first term. Now that we've got two logarithms with the same base and coefficients of 1 on either side of the equal sign, we can drop the logs and solve. So combine like terms, 6x and x. x will become negative x, which results to 6x minus x equals 5x. Then now we can simplify it by dividing 5 on both sides, so our final answer would be x equals 1 over 5. Example number 2. In this equation, we've got 3 logarithms and we can only have 2. It doesn't really matter how we do this, but since one side already has one logarithm on it, we might as well combine the logs on the other side. Now we've got one logarithm on either side of the equal sign. They are the same base and have coefficients of 1, so we can drop the logarithms and solve. Distribute x to x minus 1, so it will become x squared minus x equals 3x plus 12. Then we must equate it to 0, so we transfer 3x plus 12 to the left side, making it x squared minus x minus 3x minus 12 equals 0. We then need to combine like terms, and in this case, it's negative 3x and negative x, which is equal to negative 4x. Next, we need to factor them so we can get x minus 6 and x plus 2. So our x's are negative 2 and positive 6. No logarithms of negative numbers and no logarithms of 0, so this is a solution. Be careful here. We are not excluding x equals negative 2 because it is a negative. That's not the problem. We are excluding it because once we plug it into the original equation, we end up with logarithms of negative numbers. It is possible to have negative values of x solutions to these problems, so don't mistake the reason for excluding this value. Also, along the lines, we didn't take x equals 6 as a solution because it was positive, but because it didn't produce any negative numbers or 0 in the logarithms upon substitution, it is possible for positive numbers to not be solutions. So, with all that out of the way, we've got a single solution to this equation, x equals 6. Example number 3. To solve this, we need to get the equation into exactly the form that this one is in. We need a single log in the equation with a coefficient of 1 and a constant on the other side of the equal sign. Once we have the equation in this form, we simply convert to exponential form. So, let's do that with this equation. The exponential form of this equation is 2x plus 4 equals 5 squared. And remember how we got 25? It's because 5 times 5 is equal to 25. Notice that this is an equation we can easily solve. 2x plus 4 equals 5 squared becomes 2x plus 4 equals 25. Then we need to combine like terms. That's why 4 on the left became negative 4, or 2x equals 25 minus 4, which then equals to 21. The next thing we're going to do is divide both sides with a number beside x, which is 2, so we can cancel 2x over 2, leaving only x, and so our final answer is x equals 21 over 2. Only positive numbers in the logarithm, and so x equals 21 over 2 is in fact a solution. Example number 4. Let's get the logarithms onto one side and combine it into a single logarithm. So log base 2 times x squared minus 6x minus log base 2 times 1 minus x equals 3 will become log base 2 times x squared minus 6x over 1 minus x equals 3. Now, let's convert it to exponential form. X squared minus 6x over 1 minus x equals 2 cubed can be simplified into 8 as 2 multiplied by 3 times is equal to 8. Now, let's solve this equation. We need to distribute 8 to 1 minus x, so that becomes x squared minus 6x equals 8 minus 8x. Then, we need to combine like terms, so negative 8x becomes positive 8x, and then we subtract that positive 8x with negative 6, which gets us to positive 2x, or x squared plus 2x minus 8 equals 0. Then we factor it out again to get x plus 4 and x minus 2. So our x's are negative 4 and positive 2. Now, let's check both of these solutions in the original equation. So upon substituting in this solution, we see that all the numbers in the logarithms are positive, and so this is a solution. Take note again that it does not matter that the solution is negative. It just can't produce negative numbers or zeros in the logarithms. In this case, even though the potential solution is positive, we get negative numbers in the logarithms, and so it can't possibly be a solution. Therefore, we get a single solution for this equation, x equals negative 4. Example number 5. In this case, we've got two logarithms in the problem, so we are going to have to combine them into a single logarithm as we did in the first set of examples. Doing this for this equation gives. Now that we've got the equation into the proper form, we convert to exponential form. Recall as well that we're dealing with a common logarithm here, and so the base is 10. The exponential form of this equation is x times x minus 3 equals 10. So that becomes x squared minus 3x minus 10 equals 0. Remember to factor them again to get x minus 5 and x plus 2. So our x's are negative 2 and positive 5. So we've got two potential solutions. Let's check them both. We've got the negative numbers in the logarithms, and so this cannot be a solution. Let's check x equals 5. Since there are no negative numbers or zeros in the logarithms, this is a solution. Therefore, we have a single solution to this equation, x equals 5. That is all for today. I hope you guys have learned something about logarithmic functions and how to solve them. Thank you for listening. We hope we have done something to help you understand this lesson.